Good morning, everyone. I want to welcome you to another uh, statistic class. Of course, today the focus is going to be on matrix decomposition. I remember on Monday we started this particular topic that we call linear algebra. Of course, linear algebra actually play a very huge role in analysis of multivariate data. So Monday I introduced you to uh, you know matrix algebra, where I walk you through transpose, the inverse, the product of two matrices, two vectors, and so on, like that. So we don't just do all of that for fun. They have application in multivariate analysis. So by the time we go into multivariate technique, you're actually going to begin to appreciate what we're doing now. Okay, so what we're doing now is very, very crucial. So today, like I said, the focus is going to be on matrix factorization or matrix decomposition. Okay, so we'll be following this particular outline. Um, we have succeeded in accomplishing one and two, and of course, we are on three today, which we call matrix decomposition. And under the matrix decomposition, so the focus will be on eigenvalue, Poleski decomposition, singular value decomposition, QR, and so on, like that. And after showing all of that, I'm also going to uh, you know, give you information about the areas these are applicable or in real life. Okay, so going into matrix decomposition now. Okay, now let me tell you this. I remember in high school, when you see something like this, for instance, you see something like this. Now, in high school, when you see something like this, we have a function that is being factorized, and this particular function is actually being factorized, into two separate entity, and in such a way that if you look at the split at the right hand side, multiply them will give you exactly what you have on the left hand side. Now, what we want to do today, um, we want to look at a matrix. Okay, it's just like looking into a data structure, and we believe that on that, splitting a data structure we actually lead us into uh, uh, you know extracting insight that we need to understand our environment. So we want to extend this gesture of decomposing uh, into matrix. Okay, so like I said, when you are learning, you need to first ask yourself question. Okay, so why is matrix decomposition significant? Okay, what is the essence of decomposing matrix? Okay, now the essence of decomposing matrix, at times we may actually want to solve system of equations. Because in multivariate analysis, where the number of parameters involved is going to be more than one, there's possibility you're actually going to have more than one equation. So having more than one equation, so how do we solve a system of equation simultaneously in order for us to be able to obtain the parameters of interest? So I'm actually going to say the idea of matrix or decomposition is going to work in that direction. So solving system of equations. Now, another reason why we go for matrix decomposition is we want to obtain a low rank approximations. What do I mean by low rank approximation? Please, I need you to pay attention. Okay. You know, in image processing, where you have your image, the image contains a good number of pixels. And of course, the image, every image has a dimension, right? And of course, the just like you see an image and the original image is going to have full rank. I'm going to say that again. The original image is actually going to have full rank. But why at times, because of problem of data storage, because I'm going to say that again, because of problem of data storage, we may actually want to reduce the image. We want to compress the image in such a way that we're still going to see the image is not going to lose the total quality. Okay. So if you are trying to do that, why are you reducing that? You're reducing that, you're reducing image, you're reducing rank, you're reducing dimension, and you're actually going to save a storage or, space, because the more dimension of an image, the more space required. And of course, you're going to spend resources, for you to be able to store your data. And the question now is, how do I reduce my image in such a way that I'm still going to maintain some quality? Okay, that's what we call a low rank. Okay, the original image has a full rank. Okay, the idea of matrix decomposition can now achieve a low rank approximation. Okay, so I'm going to walk you through all of that. Then another important, another significant reason why we decompose an image, okay, is finding important features of data. Let me tell you this. Data are contaminated. I'm going to say that again. Every data set is contaminated. So if I have features, I have so many features, it's not necessarily going to be all features that are important. I'm going to say that again. And I have features that I call explanatory variables. It's not going to be all of them that are important. The question now, can we have a dimensionality reduction technique that can actually, you know, extract the important features? I want to extract the important features. I want you to take a look at this. If I decompose my matrix, the original matrix is contaminated in nature because the original matrix actually is giving us a sense of data structure that is contaminated. Now, splitting that, okay, you'll be able to extract the noise out. Extracting, filtering out the noise, then it means you'll be able to extract the most significant features. That's what it means. Without matrix decomposition, there's no way we'll be able to do that. Now, you now understand the reason why we do what we do. Okay? We don't just do what we do. We got reason, why we do it. Now, I just gave you the reason for matrix decomposition. Now, let me tell you this. Some students, they have phobia. for mathematics, they have phobia for statistics just because they don't really understand what they are doing. Like they don't understand the reason why they do what they are doing, even though they have a mathematical knowledge of doing things, but they don't really understand reason why they do what they do. If you understand reason why you do what you do, you will appreciate more what you are doing. And that is why before we go into mathematical aspect, we need to first, highlight what are the benefits that we're actually going to gain from splitting or decomposing our matrix. Does that make sense? Okay. Now, what are the matrix can be decomposed in different ways depending on the kind of technique we're using. Now, I present to you four uh, you know, uh, common matrix decomposition approach. Number one, the eigenvalue decomposition, the Koleski decomposition, the singular value decomposition, then the QR decomposition. But let me tell you this, these are not the only decomposition technique that we have. There's so many of them. But right now, in this lecture, we actually want to focus on this four. Now, what I want to do right now, I promise that what I want to do right now is going to be complicated, but I want you to follow what we want to do now with a mathematical mind and with a practical mind. You already know the reason why we want to do what we want to do now, why we want to decompose our matrix. Now, we want to have an, eigenvalue decomposition now. Now, I need you to pay attention. Okay, take a look at this guy. That guy is actually a matrix A. A matrix, in fact, is a square matrix. How do I know it's a square matrix? I have n by n. You can see n by n. The numbers of rows and numbers of columns are the same. This is more or less like having the number of observations equal to the numbers of features. For what I'm seeing here, the multivariate data structure. Now, I have a matrix A. Okay, in the decomposition of a matrix, we can split matrix into two or three or even more than that. But by eigenvalue decomposition, it's actually going to split matrix into three splits. Take a look at what we have right now. And I need you to pay attention to equation 10. Okay, we got three smaller matrices from the split. If you take a look at the first one, okay, the very first one is actually the eigenvector. Okay, that notation is the eigenvector. Okay, and of course, if you take a look at the split in the middle, is actually the one I call lambda, the diagonal. Of course, you know what diagonal matrix is. I show you diagonal matrix on Monday, and I wanted to picture that in your mind for you to be able to understand what I mean here. Okay, eigenvalue, okay, is the element in the diagonal. Okay, this is applicable in principal component analysis. In this class, there's going to be a topic committed to principal component analysis. Okay, where we got features, variables. Okay, there's so many of that, and we're looking for a way to reduce dimensionality. Okay, and because of that, we want to use the idea of a spectral decomposition, eigenvalue decomposition. And of course, the lambdas here is actually going to represent the variance of each feature, variance of each feature. And the way it's going to do it, it's actually going to say, okay, it's going to start with the most important feature. If you take a look at this guy now, oh my God, lambda 1 greater than lambda 2 greater than lambda 3, and so on like that. It means the lambda 1 has the largest variance. The largest variance indicate the largest contribution. But you know what? I'm going to give you more information about that when we start that topic or principle component analysis. But you know what I'm trying to do right now? What I'm trying to do right now, just to make a sense of what each of these sub matrices represent. The one in the middle is a diagonal matrix. Of course, when you take a look at the one at the other side, when you take a look at this guy here, you're actually gonna see that was computed from the first one. If I know the first one, I'll be able to know the third one by using the knowledge of transpose. You can see the reason why on Monday I walk you through a transpose of a matrix. Let me tell you this. Those who have problem with you know, maybe in master's research in mathematics, statistics, or any mathematically related subject, those who have problem with masters and PhD, they actually have problem with mathematics. So I remember when I was doing my master's and PhD, I pay more attention to mathematical principle because, masters, you know, uh, sorry, can you just give me like 2 minutes? My mother is calling me from Africa, so if she doesn't just call, just 2 minutes. Thank you so much. Just everything is fine. No call up back. Thank you. Transmission. Okay, so what I was trying to talk about is if you take a look at the third one, you're actually gonna see is a transpose of the first one. And of course, what we mean by transpose is converting row to column and column to row. Now, when you take a look at what we have succeeded uh in actually splitting this particular matrix. But let me tell you this, you are not going to do this manually. You're actually going to use, of course, you have a way, you can achieve this with software. Does that make sense? So that's why we have software. Okay. Now, that is that. Now, going into Koleski decomposition. The Koleski decomposition. Now, I want you to see the difference between the eigenvalue decomposition that we did and the Koleski decomposition. The Koleski decomposition, on the other hand, we're also talking about this matrix, a square matrix, n by n. Okay, is going to split of decompose matrix into two components. But when you take a look at this guy, what is the difference between this guy and this guy? The first one here split the matrix into three. And let me tell you this, each of the sub-matrices here, okay, does not have any connection to the one here at all. The decomposition here actually, you know, is into two. As you can see, the decomposition here is into two, okay? But what does each of that represent? Of course, I know the head. Take a look at the head. Okay, it's what we call the lower triangular. Take a look at that. And let me tell you this. If I take the transpose of a lower triangular, I'm actually going to have upper triangular. So this is like splitting matrix into lower triangular and the upper triangular. Does that make sense? Upper triangular matrix is a transpose of a lower triangular matrix. Now, when you take a look at equation 11 now, even though, take a look at this, beautiful, we are decomposing the same matrix. It is the same matrix n by n, the same data structure. Okay, if you take a look at the first one, by eigenvalue decomposition, that's actually decompose it into three, with each of those subset having something different from what I have right here. They are not the same at all. Does that make sense? Now, this is called a lower triangular matrix because uh, if you go up, okay, if you leave the diagonal and you go up, every other element is going to be zero. That's why it's called lower triangular matrix. The upper, on the other hand, okay, take a transpose on the other hand, you're actually going to have that. Okay. Now, I want to go into another decomposition now. Another decomposition is what we call singular value decomposition. Now, in the singular value decomposition, now I'm going to tell you the difference now. We are no longer using a symmetric matrix. Oh, sorry, we're no longer using a square matrix. Take a look at this guy. It's no longer a square, n by p. But in the first two, if if you take a look at this guy and this guy, okay, if you take a look at this, that's a square matrix, right? Take a look at the second one. That's another square matrix, right? But when it comes to this guy, it's not a square matrix, not necessarily a square matrix, n by p. Now, and that is the reason why, if you take a look at this Koleski decomposition, okay, this can be used to solve a system of linear equation. Okay, now take a look at this. If I have three equations, there will be three unknowns, right? And if I have three unknowns, then it's gonna require a square matrix, right? 3 by 3. Does that make sense? Four equations, four unknowns, and so on like that. Okay. Now, coming back to singular value decomposition, you can see right now the matrix is no longer square. The matrix is actually maybe kind of rectangular, and we are actually decomposing this into three. Okay. Now U S V transpose. I needed to take a look at the first one. This is also good for it has a very good application to image processing as well. Or particularly if you want to talk about surveillance video application, where you actually want to separate motion from a static background, stuff like that. Now take a look at this. The U here, okay, is another matrix n by r, and we call that left singular vector, okay, and S is the diagonal, okay, and V is actually the right singular vector. Now, there's a connection between singular value decomposition and this guy. There's a connection between them. Because when you look at the matrix in the middle, it's diagonal here. And if you look at the matrix in the middle here, oh my God, S is also diagonal. Take a look at that, which is a singular value. Does that make sense? Okay. So when you take a look at this is the decomposition. This is what we call the singular value decomposition. Now, if you remember what we said on Monday about having a full rank or something, for instance, if you take a look at R here, which is less or equal to minimum of M and N, and R is equal to minimum of M and N if A is a full rank. So which means we are not interested in a full rank. Here, the idea of decomposing this matrix, the interest is not on the full rank. The interest is to get a less, a partial rank. Okay, because when a full rank, in the image processing now, a full rank is the whole picture, the original picture, the original image. The original image is taking a lot of spaces in the storage. We want to reduce that. Reducing a full rank, then you're actually going to end up getting a low rank. And that is why this is very good for a low, when you are looking for low rank approximation. I want to lose some kind of, pieces, but it will not drastically affect the quality of my image. So why am I reducing that? I'm reducing that because of space. Maybe I'll be able to save space. Okay, the more space that you use, the more resources. We want to save our resources. Okay, how can we reduce this image in that so we're using the idea of mathematics. Let me tell you this. I used to tell people around me, if you really want to understand the world, we need to have a mathematical mind. We need to leave this world mathematically. Leave the world mathematically. So the way to understand the world, because understanding the world, because the world itself is mathematical in nature, understanding a mathematical structure requires a mathematical mind. And if there's a problem in the world, maybe we have problem with math. That's my conclusion. Does that make sense? Okay. Now, U and V are column-wise orthogonal, and this have to hold in such a way. Of course, this is a property of mathematics. If I use the transpose of a matrix to multiply the original matrix, it give me identity. Okay, so if that happen, then we're going to say U and V are orthogonal. Or if you are asked to investigate the orthogonality, okay, how do we investigate orthogonality? Okay, so U prime U, that is U transpose U, must be equal to V transpose V, must be equal to identity. Must be able to verify that. Now, I want to go into QR decomposition. Now, in a QR decomposition, okay, we actually want to decompose any long, take a look at that. We can be used for n equal to P or n greater than P, okay? And so, take a look at that. It's like partitioning matrix A into two entity, Q and R, okay? And Q is orthogonal matrix, and the R is what you see, which we call, the arrow is the upper right triangular matrix. So the arrow here is the upper triangular matrix. But like I said, you don't need to be worried about computing this. So I'm not gonna ask you to do the computation manually. Of course, you all have the knowledge of software. There's software around that can actually handle this. But there is one thing that should point your direction to any of these. You don't just choose a decomposition approach or technique arbitrarily. I'm going to say that again. We don't just choose a decomposition technique arbitrarily. We actually need to have a guide before we make a selection. And that is the reason why you need to be able to understand the application area of each of these techniques before they can be chosen. You don't just choose them. Okay, this technique don't solve universal problem. No. Okay, and that's why you need to be guided before choosing them. Okay, now because of that, away from the mathematics now, I'm going to go into this essence of matrix decomposition in statistical learning. I believe I started with this, trying to tell you the essence of the matrix decomposition. Because let me tell you this, if you don't know the essence of the decomposition, why are you doing it? Why? That's the question I used to ask. I don't just do maths. Okay. What do I want to bring out from what I'm doing? What do I stand to gain? Does the society stand to gain? Now, take a look at this. I want to, so uh, when we have a dimensionality issue, in statistical analysis and in machine learning, when machine learning world, where we got a lot of features, a lot of variables, okay, that you want to learn from, okay, and of course, we normally run into dimensionality issue. Now, when we run into dimensionality issue, okay, we actually need an approach that will reduce the numbers of features in my variable in my model in such a way, in the data structure in such a way that I don't lose greatly. Let me tell you this. When you reduce, okay, there's going to be a loss of information because we want to reduce. But how can we reduce in a way that we can minimize the loss? There's always going to be loss. But how can we minimize the loss? And that's why we need to visit, techniques of matrix decomposition. Now, the principal component, there's an approach, there's a technique, okay, that I'm still going to walk you, that we're still going to do in this course. We call that principal component analysis. But let me tell you this, the principal component analysis actually use singular value decomposition. And of course, the singular value decomposition, I've already talked about this guy here. Okay, the principal component analysis actually rely on singular value decomposition. Now, what is the intention with the principal component analysis? The principal component analysis, we normally apply that when we want to reduce the dimensionality in our data structure. I got so many features. Now, is there a way I can actually reduce that in such a way I'm not going to lose totally? We're still going to retain features with significant amount of information. Okay, so the principal component analysis uses, take a matrix decomposition technique called singular value decomposition. I'm going to walk you through that by the time we start that topic on, principal component analysis. I have an example here. When you're trying to analyze high dimensional gene expression data, okay, there's so many features, thousands of features in the gene expression data. And what you want to do is to reduce these thousands of features into few principal components. There's so many of them, but you want to reduce that. Okay. And that is one of the example here. Okay. So principal component analysis actually use singular value decomposition technique, which is one of the matrix decomposition technique. Now, data compression. I think I've given you an example of that image. I want to compress my image. I want to compress my data. Compressing data, you will lose some information, but we actually have a way to minimize the loss. We can't help it out. We find ourselves in a world where if I actually want to extract information from data, okay, using the best model, using the best algorithm, you are not able to extract 100% information. No, there will be information loss. George Box actually acknowledged that. And that was why he said model is not the same as reality. Model is an approximate reality, not model does not give us an exact characterization of reality. No way. There's going to be a gap. We acknowledge that. But we're trying to minimize the gap. So in data compression, okay, I want to compress my image, okay, in such a way that I don't lose the total quality. Then I can use a low rank approximation like SVD or QR. You know, the other time we talking about QR, right? I'm going to take you back. This QR, very useful in image compression. Does that make sense? Very useful. Okay, in image compression. Now, so that is data compression. Okay, so that can be used. And I said, you know, allow us to represent a matrix using fewer components without significant loss of information. Look at that, without significant loss of information, which means we got loss of information, but not significant. I think I've been talking and talking. Is there any question? Are you sure you are all enjoying my party, right? The statistical party. If you're not enjoying my party, please ask question. If you get stuck, please ask question. Okay, now I want to go into another one. Noise filtering and signal extraction. We do that a lot, you know, in time series analysis. Okay, we do that a lot in predictive modeling. We do that a lot in statistical modeling in general, where I told you data set are contaminated. Our model, you actually want to have a way to extract, you know, the signal. The signal is the pattern in the data that you need. Okay, and in a way you want to filter out the noise. What makes the data set to be contaminated is the noise, and you want to filter it out. That's what makes data set to be contaminated. And take a look at this. The idea of matrix decomposition is going to work because the old matrix, the old data structure, don't forget, matrix represent data structure. If data is contaminated, matrix is contaminated. Therefore, need to be decomposed. And that is why the idea of matrix decomposition is going to work here. So by separating signal, oh my God, signal is the important features, important component, the trend, the pattern that we need, the information that we need. You want to separate that from the noise. The noise is going to be singular values. That's why in the singular value decomposition, okay, I'm going to take you back. I'm going to take you back. How am I going to know some features have smaller values and some figures? I will be able to know through what you actually take a look at this guy. Uh, let me to better your understanding. Let me go here. Okay, take a look at this guy. Do you see that? Lambda one, lambda one is greater. Lambda one is the variance of the first feature. It's trying to tell you the first feature is the most significant one because it has the high variance. Variance in principal component analysis is contribution. Does that make sense? Variance in principal component analysis is a contribution. So when you look at that, lambda 1 greater than lambda 2, it means lambda 1 is the greatest. The smallest lambda here is a lambda n. So the lambda n is a variance of a particular feature. What is telling you that feature is not that important? It's less important. Does that make sense? Okay, that's what I mean. Okay, so um, so noise filtering and signal extraction, we use SVD. So singular value decomposition can filter out the noise. Okay, the next one is a latent factory discovery. Okay, this was not part of the technique that I discussed today. I told you there are still different kind of matrix decomposition techniques that we have. Okay, there's one that we call non-negative matrix factorization. The non-negative matrix factorization is going to decompose matrix into smaller pieces, but it's going to say that each matrix is have to be non-negative. Talking about the part, okay, has to be non-negative. Okay, now this is very useful in topic modeling. Topic modeling, okay, topic modeling. In topic modeling, where we actually want to understand where, when you look at the matrix, it's actually going to be a combination of document and words. In this document, how many words? Okay, and if you look at article, you could have article, maybe look like a newspaper, for instance. Newspaper, there's going to be a section where they discuss sports. There will another section is politics, another section in economy. Does that make sense? Now, for instance, looking at a group of words in an article, let us assume that we don't know whether it is sport or politics or economy, but looking at the group of words, for instance, maybe I actually look into a newspaper and I saw no the numbers of free kicks, the numbers of penalties in them, and I saw the numbers of fouls, then I would definitely know that they are talking about sports. But when I look at another one and I see, something on maybe a candidate actually talking about his manifesto and so on like that, and I know that's centered on politics. Okay, so there's a way we can actually partition a document, a document and word matrices, into simpler matrices in such a way to uncover what we call a latent factors. Okay, and let me also tell you this. There's a particular topic we're also going to talk about. We call it factor analysis. If I have so many features, okay, and relationship exists among the features. Now, is there a way we can we have a way to extract some hidden factors that could explain the reason for the relationship among features? I'm going to say that again. We have we got some features, and these features are related. Okay, they depend on each other, just like what we normally have in multivariate analysis, where features depend on each other. Can we actually identify hidden factors, okay, that could be responsible, okay, for for that? Okay, that's what we call latent factors. If we're able to do that, then that will enable, that will enhance interpretability. Does that make sense? Now, another one, clustering and community detection. Okay, clustering and community detection, there's a particular area in statistical learning where we actually uh, want to we believe that objects as are heterogeneous in nature, they are not supposed to be in the same class. Is that a way we can partition them into different clusters in such a way that in each cluster, okay, they are more or less the same? Okay, we actually do this a lot, when when you want to apply to crime analysis. When you do crime analysis, where you actually collect data over states, and in each state you actually you collected data across variables, type of crime, the type of crime, like in the state of Minnesota, murder. You talk about assault, rape. You talk about the urban population in that state. So in each state, maybe in the United States, you're actually focusing on what I call time, the type of crime. Now, you now want to group states in terms of crime. You want to group them. Okay. Grouping states now is to actually, you need the knowledge of clustering. The clustering means grouping. Okay. There's possibility. maybe in times of rape or assault, some state may be in the same group. That's what we call clustering. Okay, so spectral clustering actually uses eigenvalues and eigenvectors, okay, from matrix decomposition, okay, of the Laplacian matrix to identify clusters. So we have a way to identify clusters, or you want to identify hotspot, crime hotspot, okay. You're like, areas are not the same when it comes to crime, and that's why you're actually going to see police presence more in some areas than some areas. Does that make sense? They don't just go out. Okay, they don't just go out. So they actually do advanced research before they go out. Okay, recommender system. Okay, the idea of a matrix or decomposition is going to be used here. Okay, there was a competition organized by Netflix where they want to recommend movies to their customers, and they have a matrix that is not complete because if I have so many customers, okay, if I have customer customer 1, 2, 3, 4, and 5, okay, and this is movie A, this is movie. Okay, this is movie A, B, C, and D. Okay, if this customer is me, okay, if maybe I watch this movie, okay, maybe 1 out of 5, I want to rate the movie. Maybe I rate this movie 4. If I don't watch this movie, this is going to be missing. Does that make sense? So this is going to, if I don't watch this one, that is going to be missing. If I watch this one, I'm going to put maybe this. So if you take a look at the matrix that we're going to have, the matrix, we're going to have some elements missing in the matrix. And moving forward, okay, we need to have a complete matrix, okay, before Netflix can recommend, okay, and that was why Netflix actually they organize a competition where they want this group of researchers to estimate what is missing. That's what we call matrix. The approach is called matrix imputation. Some elements are missing in the matrix, and of course, we can actually use alternating least square, SVD, all of that. They are approach of matrix decomposition. So, which means matrix decomposition technique can be used in inputting missing elements in matrix. Okay, optimization in machine learning. Okay, maybe what do I mean by optimization? Okay, maybe I want to minimize loss, or I want to maximize a function. Maybe I'm using the method of maximum likelihood. I want to estimate parameters in my model using the method of maximum likelihood. Then that will mean I'm seeking maximization problem. Okay, so Koleski decomposition and QR, okay, because they solve that, because that's a problem of equations. I want to minimize a function, or I want to maximize a function. I'm actually targeting function. Okay, of course that can be used. Okay, there are critical optimization algorithm that we use in regression and classification. Lastly, graphical models. Okay, graphical models. Okay, in graphical model we also use a graphical models, for those of you who did a 4051, of course, in 4051 we did a graphical model. Okay, situation where we use the idea of network analysis. Okay, we benefit from conditional independent and conditional dependent, and we're able to save a lot of parameter or space. Situation where we realize the variable, I mean the relationship between two if two variable, if they are conditionally independent, then it means we can just assume 0 for that. Okay, so so the idea of agent decomposition also work in graphical models. Okay, this is where I'm actually going to stop. So what is going to be next on Friday? I'm actually want to show you what we have left on Friday is miscellaneous topics. Okay, miscellaneous topics where I'm going to talk about what is the meaning of definiteness, what is the meaning of determinant in multivariate analysis, what do we mean by inverses, what do we mean by singularity, and I'm going to show you some R codes. Okay, I'm going to show you some R code. Okay, so this way I'm actually going to stop. Make sure you all stay safe and have a lovely day. See you on Friday. Bye for now.